Hi there, I'm Brian Anderson. I'm the UIL Chemistry Director, and I also teach chemistry at the University of Texas at Austin. So first of all, thank you for being UIL Science Coach. We really appreciate the time and effort you put in to help the kids. In this video today, what I want to do is talk a little bit about my process in making up the exams and share some ideas that I hope you'll find helpful in your role as a UIL Science Coach. First of all, there's a couple of other videos that I want to make sure you're aware of. Our Capital Conference last June was online, and we did a recording of a Zoom meeting for that. You can find that by Googling UIL Capital Conference 2020. When you get to that page, you'll find the 2020 conference recordings. You'll find the big red button. Just click that button, and that will send you to another page. And look in the STEM folder, choose the STEM folder, and look for High School Science Chemistry. Click on that link. And there'll be a video there where I talk more extensively about my process in making up the exams. There's a little bit of overlap between the material in this video and that one, but there's a lot of material there that I don't talk about here. So please watch that video. Also, I made up a video specifically for the students, and again, it has a little bit of overlap with what we're doing here, but it contains a lot of information that's not in this video or in the Capital Conference video. So please watch that one too if you get a chance. That one's posted on YouTube. The URL is here, or this is the title of the video. So if you just want to Google a piece of the title of the video, you should be able to find that on YouTube. All right, so a little bit of background on the test. There are 13 different content areas. These content areas, if you want a breakdown of exactly what's in each one, see the UIL Chemistry Director's Notes. You can just Google UIL Chemistry Director's Notes or Google UIL Science, and you'll find a link on that page. And it has a complete breakdown of everything that's in each one of these 13 areas, and that's all of the content area that you'll find on the UIL Science test. Now, there is at least one question from each area on every single test. So the exams are 20 questions, so there'll be 13 here, and then there'll be 7 more. So a lot of these will be doubled up, and a lot of them are crossover questions anyway. There might be one question that fits into 2 or even 3 different content areas. On the Invitational A through state exams, as you move deeper into the contest, I don't want it to feel like the student is sitting down and getting a different test every time. I want it to feel like the same test, but getting harder and harder. So what that means is I put in some scalable problems. I'll show you an example here in a minute. And there's another example in the student video. But problems where you're doing kind of the same problem, but it's just getting a little bit harder each time. The exams tend to become increasingly quantitative because quantitative problems are longer. One way to make the test harder is to make it longer to do the problems. We only get 20 problems, but if it takes you longer to do each one, the whole test becomes longer. And the calculational problems will have more steps. On the invitational exams, usually you're talking about one calculation to solve a calculational problem. But on the state exam, I can daisy chain problems together where you have to do one calculational problem, and your result of that actually goes into the next step of the problem. I can describe a sequence of events, and you end up having to do 3 different problems with 3 different equations, all to solve one question on the state exam. So it does get increasingly complex the further you move into the contest. So here's an example of what I mean by scalable problems. All of these are basically problems where we're adding ice to water, okay? Well, here's the first one. How much heat is required to heat some water from 0 to 20 degrees? And I hope that most of the students would be able to calculate the heat based on the mass, the specific heat, and the change in temperature of the water. So what then if we put some ice in the water? Then we want to melt the ice, or there is no water now. We want to melt the ice and heat the ice to 20 degrees. Well, now your heat that's required is the heat that's required to melt the ice and warm the water. So how much heat is required to, again, we're starting with colder ice. Now we have to warm up the ice, then melt the ice, and then warm up the water. Things are getting a little more difficult now. This would be the district test. That's the first competition exam. Here's the regional one. How much ice do you have to, if it's -5 Celsius. You have to add to 100 grams of water to bring the final temperature up. Now you've got two sides of the equation. You've got your water on this side and your ice on this side. So you've got to warm up the ice, melt the ice, and then warm up the water from the frozen ice. This last question, you're going to be using the same equation to solve that, but this time you're solving for T final, which makes it harder because T final appears on both sides of the equation, and that means the algebra is a little more involved. This would be like a state exam. So this is an example of what I mean by a scalable problem. We're doing kind of the same thing. We're just talking about putting ice in water and warming it up. But the problem becomes increasingly more complex and it takes longer to solve at each step along the way. So different ways that I can make problems harder. Give the chemical name instead of the chemical formula, because you've got to know the names. That's one thing that I emphasize. Don't balance the equation. I will sometimes give you a balanced equation early on, unless I'm asking you to balance the equation. But later in the contest, the equations won't be balanced. I never put in bad numbers. Okay, if there are no numbers in the equation, it's unbalanced. But if there are numbers in a chemical equation, then it is correctly balanced. I don't put in fake numbers to fake the students out. I can add more steps to a multi-step problem. This is one. Ask about a quantity that doesn't appear explicitly in the equation. For example, the ideal gas law has mass density, it has number density, it has the molar mass of the gas. All of those are hidden in there because your number of moles is grams over the molar mass. And so there's just a lot of other variables that are hidden in the ideal gas law. And a beginning student might not see that, but a more experienced student will, and they'll break that down and be able to determine those things. Also, the further we get in, I like to put in questions that require some critical thinking in order to solve the problem. And in the student video, there's some acid-base problems like that. And I've got a couple problems at the end of this video that are examples of the critical thinking that I'm talking about. First of all, you guys should not expect to know all the answers. I know that especially when we get into the regional and then state test, this goes beyond AP chemistry. This is beyond your job description. Okay, some of this you may not have seen since you were in college, and some of it you may not have seen when you were in college. So I have to look up a lot of this stuff myself to be certain. If you see questions on the test and you don't know how to do them, don't feel inadequate. It's beyond what you're normally expected to do. So we do give you detailed solutions at the meet so you can look at it and see how these problems are solved. So I want to talk about some different resources that you can use with your students, or your students can get these because we're all socially distanced right now. And the four main ones that I look at are print textbooks, study guides, chemistry study guides, websites, and some YouTube tutorial videos. I think a lot of students like to have a print textbook just to ground them, because right now so much of this stuff, so much of life right now is just, it's unanchored, and we're all kind of adrift. And this is true when the students are trying to study chemistry and they're using one online source or another online source or another online source, and they just disappear as soon as you close the tab. But if a student has a print textbook in front of them, it's concrete, it's something that can help ground them and anchor them. I know I always liked having a print textbook. So any textbook that the student finds readable is fine. And Half Price Books, by the way, they have a bunch of used textbooks for $15. You can find them in Dallas and Austin and Houston. The most recent textbooks, we don't currently use a textbook at UT right now, at least for the mainstream Chem 301. That's our general chemistry class. Our mainstream general chemistry class does not use a print textbook. But the last one we used was by a guy named Stephen Zumdahl. And I liked his book. He's written, by the way, he's written like 7 different chemistry textbooks. Some of them are by Zumdahl, some are by Zumdahl and Zumdahl, that's his wife, or Zumdahl and DeCoste. But it doesn't really matter which one you use. He's written high school, he's written AP, he's written college level. If the student finds the book readable, that's what you want. They're not going to, if the book is unreadable to them, it doesn't matter how good it is, they're not going to learn anything. Before we used Zumdahl, we used a book by Witten, Davis, Peck, and Stanley. Davis was a UT chemistry professor. We used his book for a lot of years. And then we used one by Atkins and Jones, but that was a calculus-based textbook. It's the one they use at Harvard and Rice, and it didn't go over so well with our students at UT. I wouldn't use that to try to learn freshman chemistry. It's a fantastic resource. I love that book as a reference text, but I wouldn't want to try to learn from it myself. My favorite chemistry textbook is written by a guy named Nivaldo Tro, and it's called Chemistry: A Molecular Approach. I find that book to be very complete and very readable and very approachable. So if you can find a copy of Tro's chemistry book, I'd recommend that if you can get your hands on it. That's what works for me, though, and what you want is whatever works for the student. Zumdahl is a pretty readable book, and so is Whitten Davis, Peck, and Stanley. But there's a lot of others out there too, Brady and Sinise, and there's lots. I have a stack of like 15 general chemistry textbooks. Most of them are pretty equivalent. Any one of them would be perfectly fine. All right, another thing I really like, and I really encourage people to do these, is get some kind of study guide. Because when you have a 400-page hardcover book that a student is given to study for this contest, it can be intimidating. But you can get these little study guides, and some of them are they're like big paperback books. They're like 6 inches by 8 inches, and they're paperback, and they're so non-threatening. Another thing I like about them, they're very concise and they're focused on problem solving. And so the chemistry textbooks have a lot of really interesting information in them that probably wouldn't show up on these kinds of tests, but they are the kind of thing that help encourage a student's interest. They help, motivate a student and enrich them, which these study guides just don't have. These are just focused on problem solving. But these concise problem solving books also, they can quickly focus on where you need extra help and where you already have the material down pretty good. So I'm not endorsing the two that are on this slide. These are just a couple I pulled off of Amazon. I go to Half Price Books and I look for little chemistry study guides. There was one that's for the Regents test in New York, and I look at that and flip through it. And I look for inspiration for problems, but I never take a problem directly out of any textbook or any study guide or anything like that. So you will never see it in a study guide and then see it on the test. And these study guides, the used study guides at Half Price Books, are usually $5 or $7, the little paperback books. There's some websites that I recommend using for students. One of them, this GChem, this is what we use now. This is our electronic textbook at the University of Texas. It's not a complete fleshed out textbook. It's really kind of a skeletal version of a textbook. It only covers the material that we cover in our general chemistry classes. But it has some problem solving videos. There's some good stuff on there. Some of the sections are a little more concise or a little more clear than others, but it's a good place to go if you're looking for a very nearly complete curriculum. This covers everything that we cover on the test. The 13 concept areas, those are all covered in our general chemistry class, and they are all covered on the GChem website. Also, this is brand new. Chem book. My predecessor as UIL chemistry director was a guy named Paul McCord, and he's written this online textbook called Chem Book. It's not for a general chemistry class. It's for the chemistry class for non-majors at the University of Texas. But it's a really good introductory guide, and I would definitely have your students. For high school students, this is fantastic. It's a great way to come in and get some context and some background. And then if you want to look up the same section on ChemBook or on OpenStax or something like that and get the more technical aspects. ChemBook doesn't cover everything that we cover, and it covers some stuff we don't cover. But it's a really good introduction to a lot of this material for students. OpenStax Chemistry, I think you all know about that. It's a free online textbook. It's a very good online textbook too. And if you want to, you can buy a print copy of OpenStax Chemistry. It's about $55. I think you can buy them on Amazon. Chemistry Libra Texts is another one. It's a great online resource. And this website here, it's called preparatorychemistry.com. It's by a guy named Mark Bishop. I think he teaches at a community college in California. And he has an online textbook that I really like. He explains a lot of things well. So when I was teaching the general chemistry labs at the University of Texas, I would send my students, this is before GChem, I would send them to the preparatorychemistry.com webpage for more background information. That's a really good site. YouTube tutorial videos are great. They can be passive, but sometimes a student needs to just sit and watch a video. So Khan Academy is always good, but a lot of people say they're boring, and then if your student is disconnecting from Khan Academy, then it's not going to help them. Tyler DeWitt, I like Tyler DeWitt a lot, and Chemist Nate, and they give some very basic introductory tutorial videos. So if you have an advanced student, it might not be as helpful for them. But a basic student, a student who's just learning this, if you have a sophomore who's in sophomore chemistry who's going to be taking these, that's a good way to get a look ahead at what's coming. Professor Dave Explains and Bozeman Science. Which of these YouTube channels is best depends on the student and depends on where the student is. Professor Dave Explains, he doesn't go through the material step by step the way Tyler DeWitt or Chemist Nate do. Sometimes he has gaps in what he's talking about because the students that he's addressing don't need to be told every step along the way. But if you're a student who does need to be told every step along the way, then you might get lost a little bit in a Professor Dave Explains video. But any of these, the students just need to try them and see what connects with them, what they like and what works for them. Kind of just like with textbooks. Certain things, you guys got to know these. If the students, if they're going to be taking these tests, they have got to know how to name compounds from formulas and how to write formulas from names. Whether you're talking about a covalent compound, an ionic compound, an acid, ionic compounds where you have a variable charge cation or a constant charge cation. Calculating moles from any other amount. I could give you grams and you could calculate moles. If we're talking about a gas, I can give you pressure, temperature, and volume, and you can give me moles. If we're talking about electrochemistry, I can give you the total amount of charge, and you can give me moles of electrons and then moles of whatever metal we might be talking about. Stoichiometry here, this is the big one. I should have put stoichiometry first. Our students at the University of Texas, the students who have mastered stoichiometry have such an easier time of it. But the students who haven't, they're struggling with stoichiometry at the same time that they're trying to learn other concepts. And that just makes it so much harder for them. If your students can do compositional stoichiometry using the subscripts in the chemical formula and reaction stoichiometry using the coefficients in the balanced equation, if they know how to do that, they're going to be in really good shape when they get to general chemistry. And also using equalities as conversion factors. Anything you have one thing is equal to another thing, that's a conversion factor. You can put whichever one on top of the fraction you need in order to make your units work out. But a lot of chemistry, it seems, is unit conversions. So make sure your students get a lot of practice with unit conversions. Some coaching strategies. The invitational exams, what the students really need to know for the most part for the invitational tests is just basic equations. They do have to learn all of the equations that they're going to use. We don't give them any equations on the exam. Unless I write a problem where they need something like the equation for the volume of a sphere. I don't expect them to know that, so I would give them that. But in general, they need to know the equations. And at first, just the basic equations. Later on, things are going to start to intersect. And here, this is an example of solubility and acid-base coming together. If we have a saturated magnesium hydroxide solution, we have hydroxide. Well, what's the concentration of the hydroxide from the solubility problem? That will tell you what the pH is. And we can complicate things further. What's the solubility of magnesium hydroxide in an ammonia solution? Well, now you got to, here you're calculating, where's my scribbler? Here you're calculating the concentration of the magnesium hydroxide, and from that, calculating hydroxide and pH. Here you're going to calculate, you're almost doing it in reverse. You're going to calculate the hydroxide first and use that to calculate the solubility. And I don't think we do any complexation chemistry. That's not part of our curriculum at the University of Texas. But all these simultaneous equilibrium problems are always fun to do. But I can't really go into complexation chemistry because it's not part of. Maybe I'll add it to the list for future years. But it's not on the complexation chemistry is not on the list for 2021. This one right here, acid-base problems where you have to carry out a reaction before you can calculate the pH. Our students have a terrible time with this because it's not just a problem where you have an equation to solve it. You have to think your way through the chemistry before you know how to solve that problem. And so I go through 5 or 6 of these acid-base problems in the video I made for students, where we take a weak acid, calculate the pH of the weak acid, add some strong base. Now we have a buffer. How do you calculate the pH there? Add more strong base. Now we have a conjugate base solution. How do you calculate the pH of that? Add even more strong base. Now we have some excess strong base in solution. And depending on what's in your solution, you calculate pH through a different formula, different calculation. And I also like to put on critical thinking problems because critical thinking is how you make it much harder. The students, they have to not only be familiar with the chemistry, they have to be so familiar with it that they can think their way through a problem. Here's a couple of examples of that. These are both from, and actually these are both from the state 2019 exam, and these problems were back to back. I think they were problem 2 and problem 3 on that state exam. And these are both just stoichiometry problems. So when this mass of metal carbonate is heated, it forms CO2 gas and a mass of metal oxide. Which metal oxide is it? And a lot of students are going to look at this and they're not going to know where to start. And so my recommendation is tell your students the first 2 things to do on any chemistry problem. If they don't know what to do, if you can write a balanced equation, write a balanced equation. And if you can calculate moles of anything, calculate moles of what you can. So here's our balanced equation for this. We have some kind of metal carbonate, but we don't know what the metal carbonate is. But if you look at the answer choices, all of these, this would be copper, only 1 copper with the carbonate, 1 barium with the carbonate, 1 calcium, 2 potassiums, and 2 sodiums. So what we basically have is something like a metal carbonate is decomposing into CO2 plus the metal oxide. And this M, it could be calcium, barium, copper, or it could be N2 or K2. But in our balanced equation, our coefficients are all 1. Okay? Now, the next step, and this is what a lot of students, a lot of beginning students might not get, is the number that you need to go forward from here is the mass of the CO2. And the mass of the CO2 isn't given to you in the problem. But it says we start with this much metal carbonate and we end up with this much metal oxide. So the missing mass is the mass of the carbon dioxide. So you get the mass of the carbon dioxide, I spelled carbon dioxide wrong, mass of carbon dioxide, divide that by what is 44.01 grams per mole, and that gives you the moles of CO2. And now if you can do those 2 things, if you can write the balanced equation, figure out that the mass of CO2 and divide by the molar mass and get the moles of CO2, well, that tells you the moles of the metal oxide and the moles of the metal carbonate because they're the same. So if you know the mass of the metal oxide and you know the number of moles of the metal oxide, you can take the mass of the metal oxide divided by moles of metal oxide. That gives you grams per mole. That's the molar mass, and you just find which one of these has that molar mass. Another way you could do this, I didn't think about this until much later, is you could, let me change my color here. Let's see if I can come down here. Boop, boop. What you could do is calculate the molar mass of each one of these, and also determine the molar mass of the corresponding metal carbonate, which is just going to be this molar mass plus 44.01 for the metal carbonate. And if you take the mass of the metal oxide and divide by the molar mass of the metal oxide, and take the mass of the metal carbonate and divide by the molar mass of the metal carbonate, for only one of these answers will you get the same result. And that's going to be the correct answer. Think about that. That was a way that came to me much later, well after the exam was over. Here's another critical thinking problem. This one is still a little bit more thinking. 100 grams of A2B3 reacts in a double replacement reaction with a certain volume and concentration of CD2 to form C2B3 and AD2. So if the molar mass of A is this, what's the molar mass of B? And it says these are all fictional elements not on the periodic table because the molar masses are not going to correspond to real elements. First thing you do, write a balanced equation. What do we have for a balanced equation here? A2B3 plus CD2 forms C2B3 plus AD2. Okay, so we're going to need, do I even have an answer here? Okay, good, I did. So we're going to need a 2 there and a 2 there to balance the equation. And this is something I learned as a freshman chemistry student myself, because there were so many times I had a problem on an exam and I didn't know how to do it. And I realized, well, if I can write a balanced equation and calculate moles of anything that I can calculate moles of, sometimes it looks like a whole different problem after you've done that. So we can calculate moles of CD2 by just taking 0.250 liters times 2.75 moles per liter gives us moles of CD2. And how does that help us? Well, moles of A2B3 is equal to, what is it? CD2 times 1 over 2, so it's 1/2 of the moles of CD2. So now we have moles of A2B3. Well, if we have the moles of A2B3, we have the number of moles of A2. Well, we have the number of moles of A. If we have the number of moles of A and we have the molar mass of A, then we can determine how many grams of A we have. And since it's 100 grams, we can determine how many grams of B. Once you know how many grams of B and how many moles of B, you can calculate the molar mass of B. So that's the way to go on this. The key is write the balanced equation and calculate moles of whatever you can calculate moles of. But in a problem like this, there is no formula for the students to plug numbers into. They have to think their way through. And it's just stoichiometry. It's just balancing equations and calculating moles. It's something that all of the students learn early on in a sophomore chemistry class. But being able to think your way through the problem makes it much more complicated and makes it a state-level chemistry question. All right, so I hope this gives you some idea of what I'm doing when I'm making up the tests and what your students are in for. I hope you can find some resources to help the students or have them check out half-price books. Look online. Sometimes you can find used copies of books on Amazon.com or something like that. And good luck to you. I look forward. I hope we are able to have contests in the spring. Maybe we'll have a vaccine by then and we'll all be there and life will be back to normal. That'd be great. If not this year, then next year. It's coming. It's coming sometime. All right. Thanks a lot, you guys. Good luck. If you have questions, my email address is on the website. I'm not going to say it here because who knows who's coming through YouTube. But yeah, look on the UIL website and you'll find my email address there. All right. Thank you, guys. Bye-bye.